Hopefully we can hear more clearly. All right, so one way you can think in the Fourier series we learned last time is what will be the DC component? What will be the DC component in this Fourier series? So in Fourier series, we have a derivation before that. Let's go back to here. Let's go back to here. There will be equivalently, there will be looks like this, which is having a frequency component when k equals 0, k equals 1, there will be A1, A minus 1, and k equals 2, 3, 4, A2, A minus 2, blah, 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 blah. Among these components, what will be their frequency component? So this AK is amplitude of a sine wave or cosine wave. What will be the frequency component in their sine wave or cosine wave? If you see here, then they will be looks like E J omega 0 KT, such a form, right? So in here, if you divide by like cosine omega 0 KT plus J sine omega 0 KT, the frequency component will be omega 0 times k, right? That will be the frequency of each sine or cosine. If k equals 0, that means their frequency. What will be their frequency? If k equals 0, what will be their frequency? 0, right? They will be 0. If k equals 1, then omega 0. K equals 2, 2 omega 0. And we learned that we call them this one as fundamental frequency, and this one as harmonics. Actually, second harmonics. Actually, harmonics will be called, will consider everything, but this one called high frequency component or second harmonic, third harmonic, fourth harmonic, depending on the order of the frequency. What about this? What about this? What's the meaning of frequency 0? I think some of you already know the answer because it was already covered in the power electronics course. Frequency of 0 is what? Frequency is what? This component. Because frequency will be 1 divided by period. That means if frequency is 0, then the period will be infinite. That means they never go to their value. Maybe a periodic signal, but basic assumption here is this is periodic signal. So among periodic signal, what will be a signal having infinite period? That will be DC. Straight line, right? So again, this one can be considered to be DC. So DC, fundamental frequency, and second harmonic, third harmonic, fourth harmonic. So we have one signal which is a periodic signal. We can divide them to DC, fundamental frequency, and high frequency component, having sine or cosine waves. That's the basic of Fourier series. And one thing to note here is if you know A0, what will be A0? If you find A0 from here, A0 from here, then there will be one period xt times exponential 0t, right? Because k equals 0. So this one, exponential of 0 will be 1, right? Exponential 0 will be 1. So based on this fact, we know that there will be looks like this. there will be the DC component. And DC component, look at this. What is it? That's adding a signal over one period and divide by a period, right? That will be, this is same form with average, right? Average of periodic signal is what? Adding a signal over a period and divided by the period itself. That's the definition of average. So this is the amplitude of DC component, which is the level of DC, we also call as DC level. DC, because frequency is 0, this exponential part will be 1. If you reorganize it, it will look like this, which is exactly the same form with average. So we consider that, okay, average of a periodic signal will be DC component, or vice versa. We try to find the DC component of a periodic signal, then just average it over one period. So this is another interesting and interesting findings. Note that this is only valid for periodic signal. Okay. So this is summary of Fourier transform, Fourier series by far. Questions? Yeah. Yeah. So the form you learned, the question was in power, so some of you took power electronics, some of you don't take power electronics from me this semester. So the form is slightly different in power electronics. Why? Because in power electronics, we are using, so the Fourier transform in here is general form. This is the basic. And depending on special cases, Fourier transform can be more simplified. One example is we already learned in last section, like this. If in here, in this formula, this x can be real, can be complex, no, does not matter. In special case that x is real, in special case x is real, we derive that and find out that there is a symmetric, right? So we initially have from minus infinity to infinite, right? In here, again, this is plus, I'm sorry. We can divide them into a symmetric component, say 0, 1n minus 1, 2n minus 2, 3n minus 3. In real, 2 and minus 2 can be paired. In general form, a2, a minus 2 may be different. In real part, a2, a minus 2 can be paired. So we are pairing ak, which is a1, a2, a3, to a minus k, a minus 1, minus 2, minus 3. So basically a minus 1, a1, a2, a minus 2, a3, a minus 3 are paired. And then, if you do that, then we can find out that this one and this one has relationship of those star. Star of this will be, they will look like that. Why? Because star of this will be like AK star, E star, right? And E star will be E minus J, because star means a, say, complex number, can be represented as A is real, B is real, they will look like that. You say this is X. Star of X will be A minus B, J, right? So if you have AK, E, J, omega 0, KT, if you do the star of it, there will be times E minus J omega 0 KT. Because in here, this one, there will be, say, this one will be A plus BJ. each star will be looks like A minus BJ. How we can show this? Because this part, remember this part is cosine, this part is sine. So if you change polarity inside theta to cosine minus theta or sine minus theta, this one will be look the same with the theta, right? If you have minus theta, minus sine, then sine will come out. Because of that, we can, if you switch the polarity inside here, we can have we can represent the star of this. Because the real part, which is the cosine, does not change polarity. The imaginary part, which is sine, they change the polarity. So you can do that. So in here, we can consider them as, if you do that, if you pair them, we can consider them as, right. So we write down that, okay, this is our ABJ, this is our A minus BJ. This our assumption. And in special case, when x is real, we derive that actually AK star equals A minus K, only in real. If it's considered complex, we cannot do it. So we can switch this one to A minus K. In real case only. So now we can pair them. Because this one, which is A minus K E minus J omega KT, can be considered to be that if we put minus K instead of K, they are the same, right? So we can consider them as a function of K plus function of minus K, right? And if you add a conjugate, if you add a star and its own, what happens? As this one is AJPK and this one is A minus BJK, from our assumption, this is our assumption, we try to derive this. The final value is 2A, only the real part and times 2. That's from the assumption. So we show that, okay, this is our real part. What else? Based on this assumption, we know that this is a real part of the J omega 0 KT, which happen to be only in real case that this and this have a relationship that this is K and this is minus K. Based on that, we can pair them plus and minus. So it will be from 1 to infinite. Why 0 is dropped? 0 is only 1. They are not paired. So we take out the 0. The second one becomes twice. This is the form. And if you assume AK equals AK, we have some form like that. This one transform like this. If you have another form AK, they will transform like this. And the final form is what we learned in power electronics. So this is a case that only X is real. So mathematically, we want a general form, but in power electronics, we don't use complex input, right? So it is assuming this is real, we simplify the equation. So basically, they're the same. You can solve this one this way. Got it? Okay. Other questions? So now we will bring some examples to solve it. Before we move forward, I should not erase this. We write down the equation one more time. And so let's put them in here. And let's bring up some example. First example. Assuming that, so this is our equation we will use for forever from now. Assuming that we have xt equals sine t or sine omega t? Sine omega 0 t. Assuming that we have this is our input. Question is, find Fourier series of this. How do it? So let us do one step by step. Fourier series is, this is our original signal. Transform this original signal to a sum of sine waves. That's the purpose and the function of Fourier series. So assume that we can transfer this one to assume that we can do that. Assume that we can do that based on first example, first problems. Among here, what is left? What is left? We want to know what is AK, right? There's only unknowns yet, right? Actually, we have to match this, but let's consider this one later. So, when you are asked to solve Fourier series, is often referred to that find AK, right? So let's find AK. Let's bring out this equation. Say one period sine omega 0 t exponential minus a omega 0 kt. Where to start? You have a form of integral having a sine times exponential, complex exponential. Where do we start? There's a few ways we can do it. Of course, let's do a one way. What if you want to represent the sine equal to some form of exponential j zeta? What will be? What it will be? Once again, e j omega 0 t. What is it? If you want to divide it to real part plus imaginary part, what will be their real part? Cosine what? Cosine omega 0 t, right? So cosine omega 0 t. What will be their imaginary part? Sine, right? Sine omega 0 t. So we already have omega 0 t over here. So to find omega 0, what we do here is we have similar to the conjugate case. We put minus in here, which is same to cosine omega 0 t, because actually it's minus omega 0 t, but cosine theta equals cosine minus theta, right? So we can neglect those minus, and this one becomes j sine minus omega 0 t. To simplify it, in sine omega comes out, so we can take out this minus, make this like this. Is it fair? And then to find the cosine, actually that is the next question. From here, to find cosine, what we do, we add them, right? I think we did this one in the first day of lecture. And there will be 2 cosine, so we should divide by half. If you want to find the sine, you subtract. So this one minus this one, and there will be 2j instead of 2. So you should divide by 2j over 1. Fair? You look like a question. Have you have a question? No? Okay. So in many cases, especially in Fourier transform, Fourier series, if you see sine or cosine, you intuitively change to, okay, it will be half of plus or half of minus divided by j, like this. From here, we can rewrite. The reason that we change to exponential is there's exponential here. So we want to have some match. And then, over a period, this one becomes what? 2j over 1 times exponential j omega t plus minus e minus j omega 0 t exponential minus j omega 0 kt. One often mistake is if you write very quickly to solve some problems, sometimes you miss omega, sometimes you miss k. So please be careful on that. So this one is what? Now, same. We can still write this. And this one becomes what? Exponential j omega 0 t is shared. Exponent j e omega 0 t is shared. Also same here. It exists everywhere. Only difference is if you multiply EA times EB is what? EAB, A plus B, right? So using this. If you multiply these two, there will be j omega t minus j omega 0 kt, right? So that one looks like 1 minus k form. And then, how about this? There will be exponential j omega 0 t times minus 1 minus k. So minus 1 minus k. Is it following? And then we have dt. All right. Let's erase this bottom one because we will use this in the next problem. Typo over a period. So let's divide the integration. First integration, second integration. What will be, so now the question will be, what will be the integration of this, which is e j omega 0 1 minus k dt. What will be integration of this over the period? What it will be? If you remember last lecture, we have an interesting phenomena in here. In here, because exponential j something will be t, assuming this is periodic signal, if this part is not 0, integer, then we anyhow add over a period. Period function, they come back to original value within a period. If you have an integer number, say that if you have period 1, they go back to here. They go back to here, for example. If you have integer of 1, they go back to here. So first value and second value after integration will be the same. If you have 2, then they come back twice. Anyway, they go back to this original value. So if this is not 0, 1, 2, 3, 4, whatever, assuming that this is integer, whatever, integration over a period will be 0 because they go back to original value. Only exception is what? Only exception is when they are equal, when this one is 0. Because when this one is 0, there will be exponential 0, which is 1. Right? Exponential 0 is 1, which is this case, k equals n, k minus n will be 0, exponential 0 will be 1, and integration this one over a period will be integrating 0 to t of 1, which becomes integration will be t. Remember that? Let's use this. If you see this one, you can see similar things. I'm sorry, I wrote them in a reverse way, t. So there's also t. This same form, right? Complex exponential having frequency of omega 0, which is 2 pi divided by t, and times some integer number. This one is always 0 when this one, 1 minus k, is not 0. It's always 0. Except a few exceptions that this one is 1. This is 0. That means when k equals 1. So the first integration, this is the interesting part of Fourier series. This one, we try to find a general form of ak. Many of the results come as a form as it will be a function of k, like it will be sine k, I don't know, k divided by k or something like this. Have a form of k. Many of them comes in the form like that. But if you solve it, like sine or cosine, for example, this one cannot be represented in general form. We don't have to, because many of them are 0 actually. We don't have to or constant, which we don't have to consider. So in here, we try to have A1, A2, A3, A4. And what this one shows here is only A1, they are not 0. Other than they are 0, we don't have to consider. So what do we find out? We are find out when k equals 0, k equals 1, then this one becomes what? 0, t, this becomes 0, so like this. So this one becomes t. When k equals 1. All right? What about the second integration? Let's have it. Exponential j omega 0 now minus 1 minus k t dt. Let's use this is the same form also, right? Same form. The variable are changed, but they are same form. What is it? When this one becomes 0, when this one becomes 0, then this is not 0. Which one becomes 0 over t, 1 dt, which one becomes t. When k equals minus 1, k equals minus 1. Only the case k equals minus 1, then this is true. So what if we think about the characteristics? Think about our characteristics. First of all, when k equals 1, when k equals 1, then what do we have? This first part is not 0. However, the second part will be 0, right? So when k equals 1, what you have? We will have 1 divided by t ej 1 divided by t, ej, which is constant, and then t. Because t minus, actually is t minus 0, right? When k equals 1. When k equals minus 1, what happens? The constant will be the same because this is constant, doesn't have any meaning, right? Any effect by k. This one becomes what? This one becomes what? First integration. When k equals minus 1. Zero, right? Because this one becomes 2. So integration of this will be 0. So there will be 0 minus this is t. Because minus 1 minus minus 1, so minus 1 plus 1, so this one becomes 0. Therefore, there will be t. Right? Other than that, everything is 0. We don't have to consider that. So we can write them. What is this? What is this? This is A1, right? What is this? This is A2, right? Oh, I'm sorry. A minus 1. When k equals 1, k minus 1. Other than that, everything is 0. So you can write them, okay, A1 is like this, A2 is like this. Or, if you try to find Fourier transform, we write down this form. Let's write down this. There will be summation of k, but it's only not 0 except 1 and minus 1. So, you can put them ej over the first one times t times what? K is 1. So, ej omega 0 1 times t. And then we have this, which is t over 1 2j minus t. So let's put the minus. And then what? Exponential minus j omega 0 t, because k is minus 1. Is it? And then what do we have? T overlaps, we can remove it. T overlaps, we can remove it. What left? That's the answer. Our sign is equal to this. Our sign is equal to this. Yeah? But this is a very basic problem, so this is actually very straightforward. You can see in this way. What is it? We go through a lot of calculation to reach here, right? What is it? From Euler formula, we intuitively know that this minus this is 2j sine omega, right? And divided by 2j is itself, that will look like this. So if you use Euler formula, we can derive this one directly. However, this one has a meaning. This is the simplest form. Sine and cosine is the simplest form of periodic signal. So this is one first example we solve. That means even though we use Fourier series, which is a different form, right? Different form, but they are actually exactly same to the original function, which is we have success, right? We pass through a different function, different process to solve equivalent signal, which is actually the exactly same signal, which is we have a success. This is true. And second thing is the meaning of this. The meaning of this is what? In frequency domain, if you plot it in frequency domain, what's their component? If there is k exists, k1, k2, k3, everything exists, then this one has component of 2 omega, 3 omega, 4 omega, 5 omega, other components. But in this special case, they only have frequencies of omega and frequency minus omega. One thing might make you confused in frequency domain is we have considered only positive frequency. But now we are in, that's because, similar to the question you asked on beginning of this lecture. Hello? This lecture. Because we, in the signals, in a circuit class or in mechanics class, we don't consider minus domain. We only consider the plus domain by far, right? When you plot a filter, okay, we have frequency from 0 to 10 hertz. We don't consider minus 10 hertz, right? When you go to frequency domain in this lecture, which is a mathematical lecture, talk about more basics, we consider plus and minus, which is actually not, in many cases, they are very symmetric. Likewise, what you derive in the real case. Because most of the engineering, we don't consider minus because there's very few cases that the signal is complex. Of course, a lot of signal is complex, but most cases, we don't have to consider the minus sign. But in here, because we are considering the basics, we consider plus and minus domains. In plus and minus domains, what happens? It has minus omega 0 component, minus omega 0 component, having an amplitude of what? 2j. 2j amplitude. I'm sorry, amplitude. This is what? Different polarity, so they're pointing minus 2j. So this is another form when you see in Fourier transform. In case of frequency domain, when you change sign, they have frequency component omega and minus omega, which is true because sine omega 0 has frequency component omega 0 only, right? And they have actually different polarity. In sine, let's consider cosine. Second question is, let's find Fourier series of cosine. So what we change? We change this one to cosine. And this one changed to cosine. What will be the difference? What will be the difference? If you see this and this, what will be the difference? We don't have j, so this is 2, now 2. And this will be plus. That's the only difference. The basic form will be the same, right? If you follow it, this one becomes 1 divided by 2, this one becomes plus, and this one does not change, meaning that this one's still valid. This one's still valid. The first one is not 0, only k equals 1. Second one is not 0, only when k equals minus 1, right? Those the value are still valid, except there is some value of difference. There will be, instead of 2j will be 2. Instead of 2j, there will be 2. And what will be difference? As there's plus in here, there's plus in here. Now, the final form will looks like 2 over 1 e j omega 0 t plus 2 over 1 e j omega 0 t. I'm sorry, minus. So this is our sine. This is our cosine. So if you say we have a meaning, so please note that this is considered to be an amplitude, but amplitude we know about by far is real, right? But yes, last lecture I explained that this AK, which is, I used the conceptual meaning that this is amplitude, but it doesn't have to be real. Because this one defines how much the volume of the component exists. So don't have to be the absolute value. So meaning that, so this is sometimes confused me a lot when I was a student, when I learned about this lecture, because one professor comes in, okay, this amplitude 2j, this is amplitude minus 2j. Amplitude of 2j doesn't sound right, right? But please remember that this way. This one is conceptual amplitude. I would say conceptual amplitude. Conceptually, how many the volume, how many the component exist. Don't have to be absolute value. You can view it as how spread them in complex domain, for example. So you just consider that, okay, this one has component in amount of 1 divided 2j, having different polarity. What about cosine? What about cosine? Domain omega 0 to 1 divided 2 minus omega 0 1 divided by 2. So the major difference between sine and cosine, first, they have different pointing. This one, both of them has slightly different AK, which is J difference. Or second, there is major difference. Sine is plus and minus. Plus in positive, minus in negative. Only 2 points. Cosine, they both pointing upward, they're same direction. So we will have a lot of repeating of this one. Cosine, they are same plus and minus may be different. Maybe they go both upward, sine, upward, downward together. And both of them has one frequency basically. Actually 2 frequency, but if they are real, because they are symmetry, you can consider them as a it's a one frequency, omega 0 minus omega 0. That's a similarity. Because cosine and cosine itself has omega 0 already. Okay? Questions? That will be summarized in next chapter. So next chapter, we have a list of table describing that. So the question is, if xt is odd function, the frequent domain transform, which is the kind of transform like this, they are also form of odd function. Is it right? So this is actually not frequency domain signal. Still we have t, right? Still we have t, right? So this is not, I skipped the explanation because we use this to find Fourier transform. Remember in the beginning of this chapter, we described that Fourier series is caseful only for periodic signal, and we still remains in time domain. Fourier transform is first transform we observe changing from time to frequency, frequency to time. And so this is not actually the frequency domain signal, this is actually time domain signal. However, if you find Fourier transform of this, they will look like this. So I used analogy to show this, to give you a taste. But actually, these two are not the same signal. That's first of all. Second of all, to answer your question, if odd function is odd function, even function. Yes and no. Because in case of the time domain to time domain, they are mostly yes. If you change to time to frequency, there is another function added on. So odd function still stays, but another property added on. And after the chapter 4, we have a table. After Fourier transform, we have a table summarizing that. A special case that x is special case, like x is real, x is odd function, x is even function, what happened to their Fourier transform. So please wait a little bit. Other questions? Oh, all right, let's move on. So in short, two things. Let's summarize it. We have, this is our objective. We try to change this periodic signal to sum of sine waves. And one way to do that, we have to find what's AK. So let's find AK. It's the objective of all these problems. To find AK, we put original signal to AK and solve it. And find out AK. That's all the process. Let's repeat the process one more time. Say that we have a periodic square wave. Say that our function is in time domain. We have a square wave. We have square pulse, and then this is repeating. This is repeating by a period of t. Okay, so. Let's define this one is T1, this one is minus T1. So this one looks a little bit typo, I think. So let's put T1. It is not periodic. So meaning that this one is 1 within from minus T1 to T1, and they are 0 from T1 to this period. And then this what? This will be half of the period. Oh, I'm sorry. So this will be T. This is 2T. And here is what? This is a line dividing this set and this set. So this will be T divided by T. Do you understand the problem? So basically we have this signal which is non-zero from minus T1 to T1, and they are 0 from here to here and here to here, which is half of the period. And then this set is repeating every T. Repeating T, repeating 2T, repeating 3T. They keep on repeating. So this is a periodic signal. Remember, periodic signal, we consider them as there's a set of signal in time domain. If they shift in time domain continuously, we consider them as periodic signal. So let's find out. What will we first thing we will do? We put the equation of find the AK. Let's find AK. And then let's put it like this. Let's put what in here. So if you integrate over a period, let's integrate from here to here. So we're integrating from minus T from here. Of course, you can integrate from here to here, from this edge to this edge. Of course, that's your choice, but we like symmetric. So we're starting from minus infinite, minus T divided by 2, go to here, integrate, and go to here. Let's do that. So from, wow, we spent too much time on this. Now we are integrating over only one section, one part of it. And then this one becomes what? From here to here is 0. From here to here is 0, right? So they are 0. We don't have to consider that. We only validate from minus T1 to T1. So we can consider this one to be one period from minus T1 to T1. They becomes 1 exponential minus j omega 0 kt dt. That's the function. right? Because other than that, they are 0, so we don't have to consider that. So to solve it, how we do it? We have t over 1. What's the integration of exponential? What's the integration of exponential at? What is it? Exponential, right? This? Right? So let's use this. We have exponential, some constant, we say constant, still here, and we have right, and then we integrate over a period. So to find it, let's see how you can do it. If k equals 0, this one becomes 1, right? This one becomes 1. So let's do some mathematics. Let's do some mathematics before we move on. Let's do some mathematics before we move on. Let us consider only this. Let's go together. Doesn't matter. Once again, we have this integral of that is what? Minus j omega 0 k over 1 exponential minus j omega 0 kt. And we do from minus infinite to infinite. How do we find? This one becomes t. This is not t1. This is the t because it's a period. We have minus j omega 0 k over 1, which is considered to be a constant in here. And then we have exponential minus j omega 0 k t1, right? Minus e j omega 0 k t1. Because now we put minus t1, minus will be plus. So they will have a form like this. Make sense? And then what? When you do the practice a lot, when you see this form, you can figure out one function right away. Exponential minus, exponential plus, and there's minus between them. What is it? Exponential jx minus exponential j minus x is what? Think about Euler series, Euler formula. What is it? We do it in here. Case of sine or cosine, right? The sine or cosine? Sine, right? Is minus. So we can think them, okay, exponential j theta minus exponential minus j theta is what? 2j sine theta, we just derive it, right? So using this, actually they're reversed. There's minus in here, plus in here. So we can consider that as minus j, minus 2j sine this value, which is omega 0 kt1. And then we sum them together. So we have one period 1 times j omega k minus over minus 2j sine omega 0 kt1. So, right? So, what do we have? Plus is plus. We can remove this and we can rewrite them as this one will be the AK, either AK will be 1 omega 0 k over 2 omega 0 k t1. handwriting is ugly, so let me rewrite this. So they form like this. Right? This is AK. Except what? K equals 0. What happens? This one becomes infinite. Or close to infinite, some different value. So, because K go to the numerator, if K equals 0, we cannot do this calculation. So let's take assumption that dk is not 0 and take exponential 어디요? Thank you. Right. So thank you. And then, so to go to here, we have the assumption that t is not 0. If t equals 0 is what? If t equals 0 is what? There will be 1 divided by over a period for 1. So will be 2t1 by t. That's when the case equals k equals 0. If k is not 0, then it will look like this. That's final solution. Once again, if you are given a periodic signal, and if you want to have Fourier series, what we have to find out is find AK. We have this equation and put this function to here, and consider or special cases. In this case, we know that this period, this area, and this area is 0. So we shorten the period when this is not 0, and then solve the problem. And what we often use, Euler formula. That's the reason I raised Euler formula in the first day of the lecture. And we find final solution. And if as we know AK, we can find out this, right? And what will be this omega? What will be this omega? Remember, this is the fundamental frequency. So basically the period. We learned that. So what's the fundamental frequency? 1 divided by t times 2 pi. Right? So you can switch this omega 0 to pi by t without any difference. So if you do that, then there's a kind of different. One thing to note is this form. We in the maybe second day of lecture, I introduced that time domain and frequency domain has many similarity. We define them as duality. Before we move on, any questions? This one will be homework, so you should ask questions right now if you have questions. So basically, you put the equation, find the AK, that's it. And remember, you always think about where is not 0, where is 0, and also, second, use Euler formula. Can I erase it? The reason that I use this equation is we have a form before we mention, we say there is a scale wave in time domain, they will be looks like, in frequency domain they will looks like something looks like this. Vice versa, if you have this form in frequency domain, time domain, they will be square in frequency domain. In the first day lecture, please check it. I mentioned this. This is time domain, this is frequency domain. This one is called a zinc function. Zinc. Sine, put C after zinc. This one is called zinc function. This one is important because the signal we often observe in many applications is pulse. square wave. Sequence of square wave. Maybe the period, this may be longer, this may be shorter. If you learn the power electronics, you'll figure it right away because we always use a pulse in all the lecture. If you learn about the mechanic systems, if you put a pulse, then there will be square wave, a very short square wave, right? And if you want to understand those square wave, you have to go back to frequency domain. Then the zinc function comes in. Zinc function has a form that there's sine of x divided by this x. So I have a form like sine theta divided by theta, something like this. So sine something, those something goes to your denominator. There's a form like this. You can see in here. Actually, they are not exactly the same, but omega 0 k, which is here, they go to here. So if you have sine, they will look like this. But because there is another function which is goes to inside here, go to denominator, the amplitude of sine changes by frequency, or k, right? That's the reason they look like this. It looks like a sine, having different amplitude at each frequency. So in zinc function, there is two kinds of forms. One form is like, as I said, looks like this. And sometimes people like periodic signal, so people put pi in here. So this one may be one form of it, but actually not exactly the same. This is same to what? If you use this, change this omega 0 to form like that, then they will form like this eventually. Anyways, if you plot it, this, the signal shown in here is the plotted signal of zinc function. Red is this one, blue is this, red is this, blue is this. Only difference is they also have different value in here. They still have same shape. Maximum looks like a sine wave, having a decay. They looks like amplitude going down. The sine wave having amplitude is going down to the side. It looks like that. So if you plot this, how it looks like in K. Remember, in zinc function, of course, that is not exactly zinc function, but if you plot it, it looks like they are decaying. Maximum at the peak, sine wave having a decaying amplitude. So you can see that maximum and sine by decaying amplitude like this. This is case that period odd is 4 times of T1. When you increase the period, so this one has period of 8 T1. This one is period of 4 T1. So this one has twice. This one's period is 2 times longer than period of this. So you can see they are spreading. Still, they have decaying amplitude of sine wave. If this one has 16 times, 4, 8, 6, 16. So period odd is keep on increasing. So they are kind of spreading because period is longer, that means slower signal, right? Still, sine wave have decaying amplitude, so still maintain the same similar form. Okay, questions? Before we finish, let me have one more claim. we have used, this is the special case we try to define this function. When you solve sine wave, when you solve the sine wave, I use the word success. We have success, right? That means that our original signal successfully transformed a different form using this equation. So this equation exists. That means we have success. Is it always true? No, it's not. So what this one gives you is Fourier, which is developer of this formula. He claims that any periodic signal can be represented as sum of sine and cosine, which is this equation. He claims it's always true. But other later period mathematicians did a lot of effort to find any exception cases. So actually, most of the signals we handle are true. We don't have to worry about if they exist or not. We just solve the equation. We're an engineer, we are a mathematician. But please remember that there's very big exception that this may not exist. This may not exist. How we define it? So say that xt is our original signal. xnt is Fourier series representation. When n, this large n goes to infinite, then this one is same to Fourier series transform. Fourier series representation what we have in here. Assume that we have error, if we have difference between our original signal, this is our original signal which is here, from n to n, and depending on number of n, then what this, if you subtract them, you can find error. What's their difference? If those error becomes 0, that means they are the same. We put a new parameter, say error is 0. There's several ways we can define the convergence. We'll cover a mathematician called Dirichlet, I think the German name, I'm not sure. He says, some cases, this is periodic signal, right? But cannot have Fourier series. This is periodic signal, right? This is that is repeating. This cannot have Fourier series. This is also periodic signal, but cannot have Fourier series because of the reason. So we will learn about that in next chapter, next time. So we are finishing today.